Welcome back to the Biochemistry for Health Sciences channel. This video will be video 2.0b and we'll continue talking about some of the general concepts on water and its medical applications. Okay, so the next concept, we talked about solubility last time. So now let's talk about concentration. So when you look at the lab tests, you see many of these tests are expressed in terms of concentration. So for example, here albumin level is expressed in grams per deciliter, blood urea nitrogen in milligrams per deciliter, chloride, concentration of chloride in millimoles per liter or millimolar, and then we have the osmolality expressed as milliosmoles per kilogram. These are all concentration units, various concentration units. So very important to understand what is concentration. So here are two examples of calculating concentration. Two liquids or fluids that are used quite often in the clinical world. So one of them is 5% dextrose. Dextrose is just basically another name, an older name for glucose that's used still a lot in the clinical setting. So 5%. What is its molarity? So express the concentration. So 5% is concentration. So 5% usually means, if it's not written, it means mass per volume. That means if you take 5 grams of glucose, which is the solute, okay, mix it with a little bit of water, let it dissolve. Once it's completely dissolved, then add more water, which is the solvent, and bring the final volume of the glucose solution. So here glucose is mixed with water. That gives you a solution. So bring the final volume to exactly 100 mils, which is a deciliter. And that gives you a 5% glucose solution. Okay, so that's how you make a 5% glucose solution. Now, if it was 5% weight by weight, which is less often used in a clinical setting, then you would take 5 grams of glucose and dissolve it in 100 grams of glucose, dissolve it in water so that the final glucose solution is 100 grams. Okay, so that's basically what percentage here mean. Now molarity is how much moles of solute is present in a liter of solution. So 5% dextrose solution in a liter, because that's 5 grams in deciliter, so 10 times more. Liter is 10 times more, so that's 5 times 10, that's 50 grams. 50 grams is present in a liter. Okay, now the molecular weight of glucose is 180. So 50 divided by 180, that gives you 0.28 moles. And this 0.28 moles is in a liter of solution. Okay, a liter of solution. So 0.28 moles per liter is also called 0.28 molar. This is molar. So we can say 0.28 molar, or we can say 0.28 moles per liter solution. That's the concentration in molarity. So 5% dextrose solution is the same as saying 0.28 molar dextrose solution. Physiological saline. Saline is very commonly used in the healthcare setting as well as in biological applications. Calculate its molarity. Once again, 0.9% means 0.9 grams dissolved in 100 mils. So that's 9 grams per liter. Molecular weight of sodium chloride, 58.5. Divide the 9 by 58.5. That gives you roughly about 0.153 moles. That's 0.153 moles per liter, or 0.153 molar. Okay, oops. So concentration, so basically a 0.9% sodium chloride is the same as saying 0.153 moles per liter. Okay, or in the lab test, we usually express it as 153 millimoles millimoles per liter. Okay, 153 millimoles per liter. So it's important to remember that concentration depends not only on the amount of solute. Okay, the concentration of a solution not only depends on solute, but also the amount of solvent. So here are three cases. So let's say this is 10 grams per deciliter. So that's a deciliter here. It's 100 mils. And there's a certain amount, 10 grams of, let's say, glucose dissolved in this 1 deciliter. Let's say if the body water went up in water intoxication, then instead of, let's say, 1 deciliter, the volume increased. In this test tube example, increased to, say, 1.2 deciliter. So now we have 10 grams in 1.2 deciliter. So the concentration goes down from 10 to 8.3 grams per deciliter. 10 divided by 1.2, that's 8.3. Okay, so the concentration goes down. The concentration goes down. So the concentration can go down if the volume of solvent increases, or if we have the same volume but the amount of glucose decreases. Okay, so either the solute goes down or the solvent increases. That will give you a lower concentration. The concentration goes down. And it's the opposite with a higher concentration. The concentration increases if either your solute goes up. Okay, we add more solute. Instead of 10 grams, there's 11 grams. 11 grams, but in 100 mils. Okay, that's one way of increasing concentration. Or the other way of increasing concentration is the effect of the solvent. So for in this case, going back to this example, now the solute is the same, still 10 grams, but the solvent volume has gone down to 0.8 deciliter. Okay, so instead of 100 mils is 80 mils. So 10 divided by 0.8, the concentration goes up. From 10, it goes up to 12.5. And this is what we see, for example, when we lose our water during dehydration. Okay, so very important to remember that concentration is dependent on not only the solute, but also the solvent, which for clinical purposes is water. Okay, so dehydration, for example, can affect a lot of your lab tests, your clinical lab tests. Important to keep that in mind. So concentration, most biological processes happen by the process of, or really depends on concentration. Okay, so here are just 4 examples. But there's so many things in the body that basically work based on the principles of concentration. So here, for example, in example 1, the concentration of glucose in the bloodstream, based on a concentration, that glucose goes into the beta pancreatic cell, and how much insulin that cell secretes depends on the concentration of glucose in the bloodstream. Okay, so the concentration of insulin secreted by the cell depends on the concentration of glucose in the bloodstream during that time when the cell is secreting. Okay, so this is an example of concentration. The amount of insulin that binds the receptor, let's say this is a receptor on a muscle cell, okay, how much insulin actually binds the receptor depends on the concentration of insulin. Concentration of insulin at the receptor. What's the concentration of insulin as a receptor? And the concentration of an insulin receptor depends on the concentration of the insulin in the bloodstream. Okay, so that's another example. Contraction of muscles. The contraction of muscle cells depends on the concentration of calcium. Okay, the concentration of calcium inside the muscle cell. Okay, the more the contraction, the more the calcium, the more the contraction. The lower the calcium, less would be the contraction. So calcium concentration. Okay, the concentration of potassium, the actual concentration of potassium in the bloodstream can have significant effects on the function of neuron firing as well as the function of the heart. Okay, so these are all processes that are based on the principle of concentration. Many things in the body work depend on this principle that we call concentration. Okay, so the next concept after solubility and concentration is the process of osmosis and a little bit about the osmotic pressure. Okay, so here is a well-known experiment that you've probably seen in your high school biology books or chemistry books to explain osmosis. So we have water present in this U-tube, and then there is this membrane, this semi-permeable membrane, basically a membrane that only allows water but not the solute. So here we have glucose, let's say some glucose present here. Okay, and this is what we have at the beginning. We give it some time to reach what we say equilibrium in chemistry. Give it some time and then come back after that time, and then we see the water levels have changed. This water level has gone down, this has gone down, and this has gone up. So why does that happen? Why? That means the water has moved from this compartment through the semi-permeable membrane to that compartment. Okay, that movement of water to the semi-permeable membrane to the other compartment is called osmosis. That happened due to osmosis. Okay, so osmotic pressure is simply how much pressure we need to apply to this column here so that the water levels remain the same. Prevent the water from moving in. That's called osmotic pressure. Okay, so that's the application of pressure. There are chemistry formulas to calculate osmotic pressure. Basically, molarity, and R is a constant, T is the temperature in Kelvin. Clinically, we don't do this. We don't measure osmotic pressure for clinical lab tests. So this is just a theoretical exercise, just to explain to you what we mean by osmotic pressure. So molarity here is 0.28, is 0.28. Then we have the R is a gas constant, that's the value in these units. Temperature is in kelvins, the absolute temperature, so we must add 273. If the body temperature is 37, so we add 273 to the actual temperature, and then multiply everything, and we get the pressure in atmosphere. But since 1 atmosphere is 760 millimeters mercury, we multiply 760 by 7.12, we get this number here, 5416 millimeters mercury. That's the atmospheric pressure. That's the osmotic pressure that is demonstrated by 5% dextrose. Same thing with 0.9% sodium chloride. What's the osmotic pressure? Again, you can use the same strategy and calculate the osmotic pressure. As I mentioned, osmotic pressure is not something we do clinically, so it's not important to do these calculations as a healthcare professional. Okay, but it's as a healthcare professional, you should be able to calculate certain other things such as osmolarity. So let's look at osmolarity. What is osmolarity? It's the number of osmoles, whose units are OSM or osmol, of solute per liter of solution. Okay, we'll keep this in mind when we talk about the next concept of osmolality. So how do we calculate osmolarity? Let's say for 5% dextrose, we calculated 5% dextrose came out to be 0.28 moles per liter. Okay, that means there's 0.28 moles of dextrose or glucose in 1 liter of glucose solution. Okay, so now 0.28 moles glucose is the same as 0.28 osmoles glucose. Okay, 0.28 osmoles. So basically the osmolarity of this 0.28 molar glucose is the same. So instead of saying 0.28 moles glucose in 1 liter glucose, we say 0.28 osmoles glucose in 1 liter of glucose solution. Okay, or we can say multiply this by 1,000 to give us milli. Okay, smaller by 1,000. So that's the same as saying 280 milliosmoles per liter. So a 5% dextrose solution has an osmolarity of 280 milliosmoles per liter of solution. Okay, now, so for some solutes like glucose in water, one glucose molecule in water simply gets dissolved and gives you one glucose molecule. But there are some solutes such as sodium chloride. So let's calculate. In this case, we have to look at the dissociation of sodium chloride. So if we made a solution of 0.9% sodium chloride, we calculated the molarity in the previous example, came out to be 153 millimoles per liter or 0.153 moles per liter. So basically the molarity of sodium chloride in 1 liter, there is 0.153 moles sodium chloride. However, sodium chloride, one molecule of sodium chloride breaks down into 2 particles, one sodium and one chloride. Okay, so basically there are 2 particles of that we get from one sodium chloride. One glucose gave us only 1 particle. Osmolarity cares about the particle. It doesn't matter whether it's a sodium particle or glucose particle or chloride particles, they're all the same. Okay, so only interested in what's the concentration of the particle. So for sodium chloride, because each molecule of sodium chloride gives you 2 particles, a sodium ion and a chloride ion, we must multiply the molarity by 2. So for sodium chloride, when we want to do osmolarity, the molarity we have to consider is 0.306. So the osmolarity of sodium chloride is 0.306 osmoles sodium chloride per liter of sodium chloride solution. Or multiply by 1,000, that's 306 milliosmoles per liter of solution. Okay, so osmolarity is very similar to molarity, except that you have to consider the nature of the solute. The nature of the solute. If the solute is glucose or a particle a solute that doesn't break down into different particles, then the osmolarity is the same as the osmolarity. But if it does break down into particles, then you have to consider how many particles you get per molecule of the solute breaking down. So sodium chloride in this example gave you 2 particles. Now if you had calcium chloride, then that would give you 1 calcium, okay, 1 calcium plus 2 chloride. So in that case, there'll be 3 particles formed, 3. So if this was calcium chloride, then you'll have to multiply this number here by 3, okay, because calcium chloride gives you 1 calcium and 2 chloride for a total of 3 particles. So once again, osmolarity is only interested in particles, not interested in whether it's calcium ion or chloride ion or glucose ion or protein particle. Is not interested, just how many particles. Okay, that's what osmolarity wants. Another closely related term is osmolality, lality, not larity. So osmolarity depended on volume of solution. Volume. Trouble with volume is the volume changes with temperature, since the volume of solvent changes with temperature. That's a problem with volume. Okay, so when the temperature changes, the volume changes, and therefore that affects the osmolarity. However, osmolality is the number of osmoles of solute, not in volume, but per weight of the solvent. So in this case, kilogram of, let's say, water. Okay, the nice thing about this, the kilograms, the weight of the water does not depend on the temperature or even the pressure. Okay, so the mass of the water rather than the volume of the solution. Okay, so for example, 1 mole of glucose dissolved in 1 kilogram of water will have an osmolality of 1 osmol per kilogram water. Okay, now osmolality is what is calculated in the clinical lab or is measured in the clinical lab. Okay, so this is what we measure. Our instruments measure osmolality. Okay. Now, one of the tests that is done in the clinical lab is actually a calculation of the plasma osmolality. Okay, so basically, plasma osmolarity is the osmolarity of all the plasma, everything dissolved in plasma, divided by the plasma water, kilogram of plasma water. Okay. Now, plasma water, if you take 1 liter of plasma, the amount of water is not 1 kilogram. It's only 0.930. So 0.93. Okay, and this number can decrease in various conditions such as stress, or if there's too much proteins present, or there's too much lipids present in the blood. So calculated osmolality is basically how many osmoles of sodium, chloride, bicarbonate. These are some of the major solutes that are present in the bloodstream. Glucose, urea, proteins, and anything else present in the plasma. Now, sodium is always, has something connected to it, because it's positive charge cannot live by themselves. They must attract something negative. So sodium could attract chloride, or sodium could attract something like bicarbonate. Okay, and anion. So cation, sodium, there's a lot of sodium in blood, attracts anions, bicarbonate and chloride and so on. So basically we can ignore the anions such as chloride and bicarbonate, which are present in quite high amounts, and instead of chloride and bicarbonate, we simply multiply the sodium by 2. Okay, because every sodium cation has an anion attached to it. Okay, so we can multiply the sodium by 2 to calculate this plasma osmolarity. Glucose, we put that into the equation. Urea is another one that can provide osmolarity, and we put that into the equation. Proteins contribute less than 0.5% osmolarity, as well as the other solutes present in plasma. So we can basically ignore this. We can just get rid of this. It's just negligible osmolarity provided by proteins or the other solids. So basically our equation for calculated plasma osmolarity, POSM, really depends on 2 times sodium plus glucose plus the concentration of urea. Okay. Now, we can even ignore this 0.93, and that's because sodium chloride, now sodium chloride in pure water will break down to give you Na plus and Cl minus, that's 2 particles. But sodium chloride in blood, in plasma, doesn't do that. Sodium chloride in plasma basically gives you some sodium and some chloride, and there's some undissociated sodium chloride, okay, some solid form. So basically, instead of giving you 2 particles, it gives you a small fraction here, a fraction here, and a little bit here. If I add up all these 3 particles, it comes out to be 1.86. Okay, so this effect of sodium not dissociating basically cancels out the fact that water, that there's not 1 kilogram water here, it's 0.93 kilograms. So basically those 2 effects cancel each other out. So our formula now becomes more simpler. The calculated plasma osmolarity is 2 times the concentration of sodium plus glucose plus urea. This is called the Wortley equation. Wortley equation. So if all of these are in millimolar, then we can use this equation. But if in United States we don't use millimolar quite often for glucose and BUN, we use milligrams per deciliter. But in other countries they might use millimolar, so this is a very good equation to calculate plasma osmolality. But here in US, we use this equation here. Okay, basically that converts milligrams per deciliter into millimolar. Okay, to do this, we divide the glucose by 18 and the BUN by 2.8. All right, so this is the equation, which is a very good equation, the Wortley equation, to calculate the osmolality. So here's an example of calculating the osmolality. So we're using the Wortley equation, 2 times sodium. So let's look at the sodium concentration. And the sodium concentration is 142 for this date here, for this patient. So 2 times 142 plus glucose divided by 18. What's the glucose concentration? Let's look at glucose mean plasma glucose concentration was just a little bit high, 114. Okay, so 114 divided by 18 to make the milligrams deciliter. This is milligrams deciliter into millimolar. And then the BUN was on this day was 16. So 16 divided by 2.8. And if we do that, we see a calculated plasma osmolarity of 296 milliosmoles per kilogram of water. Okay, so we have some very important lab tests that one is the use of what we call osmometers. These instruments actually calculate the real osmolality, the actual osmolality. Okay, so the normal range for plasma osmolarity is around 275 to 295 milliosmoles per kilogram water. Okay, so that's measured, actual osmolarity measured by this instrument. And then clinicians sometimes use this calculated osmolarity based on either the Wortley equation or some other equations that are out there in literature. This is probably one of the easiest and best equations. Okay, so remember this equation has quite a few limitations. Basically the formula ignores the fact that plasma is only 93% water. Sodium is not completely dissociated. You don't get NaCl, doesn't give you 2 particles. Okay, NaCl gives you only about 1.86 particles. And of course, the other solutes can also contribute to osmolarity. Okay, so this is actual osmolarity and this is calculated osmolarity. Okay, so if the normal range for osmolality for plasma is 275 to 295, then the question 0.9% sodium chloride. Remember 0.9% when we calculated it, it came out to be 306 milliosmoles per kilogram water. Why are we using 306, which is not isoosmotic? Because the normal range is 275 to 295. Well, one of the reasons for that you can see clearly is the what we talked about, the fact that sodium chloride in water, sodium chloride will break down. If you take 1 millimolar sodium chloride, it will break down to give you 1 particle of this, 1 millimolar, and 1 particle of this, 1 millimolar. Okay, so that's great. So 1 particle of sodium chloride gives you 2 particles, 1 sodium, 1 chloride. However, in plasma, 1 millimole sodium chloride doesn't break down to 2 particles. In fact, it breaks down into 0.086 millimoles per liter of sodium, 0.86 millimoles per liter of chloride, not 1. And then there's a remaining 0.14 left over. So we have a little bit of this particle, we have this particle, we have this particle. We add up all these three, and it comes out to be 1.86. So instead of getting 1 plus 1, we get only 1.86, which is 93%. Okay, this 93%, this fraction 0.93, we call this the coefficient of activity. So the actual calculated, when we actually calculate the osmolarity of 0.9% sodium chloride, we have to consider this 0.93. So if we take this activity 0.93 and then multiply what we see in outside the plasma 306, you get 285, which is isoosmotic. Okay, so 0.9% sodium chloride that is made by manufacturers for intravenous therapy is isoosmotic because of the fact that we have to consider what we call the coefficient of activity. Okay, and then we calculate what we call the osmolal activity. Okay, so there is another test that clinicians use, and that's called osmolal gap. So basically, osmolal gap is the measured osmolality, the one we actually measure by using this instrument, and minus the one we calculate. For example, using the Wortley equation, this one here. Okay, so measured minus calculated gives you the osmolal gap. Okay, the range is 0 to 15, but if we use a good formula for calculated osmolarity, this should be really close to 0, right? But unfortunately, none of the formulas are good. So you'll never get 0. You might get 0 to 2. So depending on what the clinician uses for calculating this and the nature of the plasma in the patient. So why do we need osmolar, or why do clinicians calculate osmolar gap? Changes in osmolar gap is especially useful for detecting poisoning of an individual by things such as ethanol, methanol, a lot of organic solvents, acetone, ethylene glycol, other organic solvents which are very difficult to measure in most clinical labs that do not have sophisticated instruments such as mass spec and gas chromatography and so on. And then these things are often seen in suicides or poisoning, homicides, okay? And then, of course, in uncontrolled diabetes, this formula can be useful for detecting maybe the presence of ketone bodies. So what happens is if any of these particles are present, so what will happen is let me just erase this. Okay, so if you had some other particle like a ethanol or acetone or ketone body, what's going to happen is this value is going to increase. You see, that's going to increase because the instrument is going to measure that particle. Okay, it's going to measure that particle. While the calculated osmolarity is not going to change because that particle is not considered in the calculated osmolarity. That ethanol or acetone or ketone body is not considered. So because this increases, this remains the same, the osmolal gap will therefore increase. Okay, so poisoning by organic solvents or presence of ketone bodies tend to increase the osmolar gap to greater than 15 milliosmoles per kilogram. Okay, and in alcohol poisoning, the osmolar gap can increase to as much as over 20 milliosmoles per kilogram. So this is a very nice, simple test to detect the presence of organic solvents as well as particles that we don't often see in the bloodstream. Okay, so we are going to stop here and continue with the concepts related to water in the next video, which will be video 2.0C, and there we will start talking about concepts such as tonicity. Okay, so until next time, have a good day. We'll see you in the next video.